We're continuing our introduction to particle physics, and in this video we're going to study the Dirac equation, which models free spin 1/2 particles in relativistic quantum mechanics. We're not actually going to solve the Dirac equation until the next video. In this video we're going to do a quick derivation of the Dirac equation, followed by a deep dive into the mathematical properties of the Dirac equation. In particular, we're going to spend a lot of time talking about the left and right chiral halves of Dirac spinors, how they are related to mirror symmetry, how we can project them out using projectors, and how they relate to Dirac adjoint spinors. We'll also talk about conserved currents in the Dirac equation, and also talk a bit about matter and antimatter. So, ordinary quantum mechanics is governed by the Schrödinger equation. However, the Schrödinger equation is not a relativistic wave equation, because it treats time and space with different numbers of derivatives, and the equation also changes form under Lorentz transformations. To fix this, we can try deriving a relativistic wave equation based on the mass-energy-momentum relation from special relativity. There are several ways we can rewrite this. It's common to define energy E over the speed of light c as the time component of momentum, pt. We can also write the formula in array notation using this 4x4 matrix called the Minkowski metric, denoted by eta. We can also write this in summation notation if we replace the time xyz indices with the numbers 0, 1, 2, 3. We can also replace this sum of the metric and p with p written using a lower index. It's also common to omit the summation symbols because we always know there's a summation happening when an upper and lower index match. This is called Einstein notation. Finally, if we write the momentum p as a vector, we can write p dot p equals mc all squared, if the basis vector dot products are defined using the appropriate signs. If we take the mass-energy-momentum relation and apply quantization rules, where energy and momentum are replaced by I h bar times a derivative, we get the Klein-Gordon equation. The Klein-Gordon equation is a relativistic wave equation, because the time and space components have the same number of derivatives, and the equation does not change form when we do a Lorentz transformation. Note that the partial t notation here indicates a derivative with respect to c times t, which is a convention commonly used in relativity. We can also start with the summation version of the relation and quantize that instead. This gives us a more compact version of the Klein-Gordon equation. As I covered in video 21, the Klein-Gordon equation does not have a probabilistic interpretation because the second time derivative allows probability densities to be negative, which doesn't make sense. Paul Dirac wanted to fix the Klein-Gordon equation by forcing it to have only one derivative in time, so that it could represent a meaningful probabilistic wave function. Dirac's idea was to factor the Klein-Gordon equation into two pieces, each with one time derivative. If we start with this negative version of the Klein-Gordon equation, we can begin factoring it as a difference of squares. The square root of -1 can be handled by using the complex I, but it's not clear what the square root of this second derivative operator is. Whatever this square root was, Dirac wrote it as a linear sum of first derivatives with unknown gamma coefficients in front. Following this assumption, if we multiply these two linear sums back together, the resulting 16 terms should match the original derivative operator. This means gamma t must square to +1, gammas x, y, and z must square to -1, and all the other terms must go to 0. The simplest way to make all these extra terms cancel is to make the gammas anti-commute. That is, flipping the order of two different gammas will introduce a minus sign. This means that the gamma pairs in the lower triangle here will exactly cancel with the gamma pairs in this upper triangle, which are all written in the opposite order. So given all these properties, the gammas cannot be ordinary scalars. They are new symbols which obey these special algebraic rules. These are the rules for the Clifford algebra CL13, also called the space-time algebra, which I talked about in videos 11 and 12. If we interpret the four gammas as the four basis vectors for space-time, then the mass-energy-momentum relation becomes trivial. It just says that p times p gives the squared length of p, which is mc all squared. If we put all the terms on one side, as seen with the Klein-Gordon equation, then factoring it as a difference of squares is also trivial. We just get p plus mc times p minus mc. Applying the quantization rules, we get a factored version of the Klein-Gordon equation. If we take the second portion of this equation and set it to 0, we get the Dirac equation. The Klein-Gordon equation is a relativistic wave equation for a scalar field, and the Dirac equation is a relativistic wave equation for a spinor field. Here, psi is an object called a Dirac spinor. And remember, the fact that we have raised and lowered spacetime indices here implies that there is a summation going on. We can also raise and lower these indices as we please if we use a summation with the Minkowski metric. Raising or lowering indices with this metric basically means leaving the time component alone and applying minus signs to all the space components. Now, these gammas with their abstract algebraic properties can be a bit confusing for people not familiar with Clifford algebras. It's common to write the gammas as 4x4 matrices that obey all these squaring and anti-commutation rules. There are multiple solutions for what these matrices can be, but two common representations are the Dirac basis, also called the mass basis, and the Weil basis, also called the chiral basis. So in array form, the Dirac equation looks like this. Now, this Dirac spinor has 4 components, labeled with indices 1 through 4. These spinor indices should not be confused with the 4 spacetime indices in this summation over the mu index, which are time x, y, z. In many sources, it's common to write spacetime indices using Greek letters, and write spinor indices using Latin letters from the beginning of the alphabet, like A, B, C. So we could denote the components of this Dirac spinor using a lowercase a as the upper index. I'll also mention that in the chiral basis, sometimes the 2 lower components of a Dirac spinor are written with lower dotted indices. I've already explained in video 9 that this is notation for parity transformations. Since the Dirac spinor is multiplied by these gamma matrices, we should also give the gamma matrices 2 spinor indices to help keep track of their 16 components. The first index indicates the matrix row, and the second index indicates the matrix column. So the multiplication between gamma and the Dirac spinor can be written as a summation over spinor indices like this. However, for most of this video, I'm going to suppress spinor indices and treat the array multiplication as just being implied by putting the gammas next to the spinors. When I said there are multiple different versions of the gamma matrices, these are really the same objects, but just transformed with a change of spinor basis. So the matrix components look different in different spinor coordinate systems. Now, with these gamma matrices, some textbooks just treat them as weird quantum matrices without any physical meaning. But I want to emphasize that the gammas are indeed spacetime basis vectors for the time xyz directions. They are just new versions of the 4 spacetime basis vectors that have been upgraded to obey these Clifford algebra properties. You're probably used to writing spacetime vectors as 4-component column vectors like this. These column vectors can be rotated and boosted using Lorentz group matrices applied from the left, often denoted as a capital lambda. However, this is just one representation for spacetime vectors. We could also write 4D spacetime vectors in the form of 2x2 matrices, which are just linear combinations of the sigma matrices. Here, sigma t is just the 2x2 identity matrix. These 4 vectors Lorentz transform with double-sided transformations of SL2C matrices, where each SL2C matrix uses half of the Lorentz transformation angle. SL2C matrices are often denoted with L, and they are also called spin 1,3 matrices since they are the double cover of the Lorentz group SO plus 1,3. These spin matrices can be written using trig functions along with pairs of sigmas for the rotations and individual sigmas for the boosts. We can write these matrices even more compactly as exponentials, replacing the trig functions using Euler's formula. There's another 2x2 matrix representation of 4 vectors where we reverse the xyz directions on the sigmas, using negative signs. This reversal of the space directions is called a parity transformation, and we'll talk about it more later. This keeps the rotation matrices the same, since they involve 2 sigmas and the negative signs cancel. But this will reverse the boosts since they only involve 1 sigma, and so we get a negative sign. You'll notice that, for the case of the parity-flipped transformation matrix, I've written it as L dagger inverse, where the dagger denotes the Hermitian conjugate. Here's why. If we have a rotation in the xy plane, and then do a parity transformation that sends x, y, and z to their negative versions, then the rotation is left unchanged. However, if we have a boost in the x direction and do a parity transformation, the boost does appear to reverse direction. When we replace L with L dagger inverse, this has the exact behavior of keeping rotations the same while reversing boosts. Since rotation matrices are unitary, the Hermitian conjugate is the same thing as the inverse. This means the 2 inverses cancel and the rotation is unchanged. However, boost matrices are Hermitian. This means the dagger does nothing and we're left with only the inverse, which reverses the direction of the boost. So for Lorentz transformations, the combination of Hermitian conjugate and inverse does a parity transformation, because it leaves rotations unchanged, but reverses boosts. Now let's get back to the gamma matrices. The gamma matrices are yet another way to write 4 vectors. We can write a 4-vector using a linear combination of gamma matrices, just like the standard 4-component spacetime vector. The gamma matrices sort of combine the 2x2 matrix representation and the parity transformed 2x2 representation together into 4x4 matrices. The reason that this happens is because the gamma matrices themselves can also be broken up into 2x2 blocks. In the chiral basis, gamma t contains a pair of 2x2 identity blocks, and the xyz gammas contain pairs of sigma matrix blocks. Note that the upper sigmas have positive signs and the lower sigmas have negative signs. As a result, when we use them to make a spacetime vector, we get a pair of 2x2 spacetime vector blocks. The top one with positive spatial components, and the bottom one with negative spatial components, transformed by a parity flip. Now, when it comes to Lorentz transformations, We already know how these 2x2 blocks transform, using double-sided transformations of spin 1,3 matrices, denoted by L. L can be written as the exponential of sigma pairs for rotations, or exponentials of individual sigmas for boosts. We can use this knowledge to deduce how the entire 4x4 matrix Lorentz transforms. It turns out we use double-sided exponentials of gamma pairs called bivectors. Let's see why this works. If we write the gamma vectors in their block diagonal form, we can consider what all the gamma bivectors look like as well. The bivectors are just pairs of gammas multiplied together. If we look at the 6 main basis bivectors in spacetime, we see in the chiral basis all the matrices are in block diagonal form. For pairs of spatial gammas, the matrices have 2 identical blocks of sigma pairs, with a negative sign in front. Meanwhile, a combination of the time gamma and a spatial gamma gives blocks with a single sigma, where the top one has a negative sign and the bottom one has a positive sign. Now, sending the spatial XYZ gammas to their negatives gives us a parity transformation. This ends up being equivalent to sending the sigmas to their negative versions. For bivectors made of 2 spatial gammas, the matrices are unchanged by parity transformation, since the 2 negative signs cancel out. But for the bivectors made of gamma t and 1 spatial gamma, a parity transformation will change the sign in front of the matrices. This has the effect of exchanging the top and bottom sigmas in the matrix. All of this is useful to know because of the following trick. If we exponentiate a bivector made of a pair of spatial gammas and expand it using Euler's formula, when we write out the matrices, we see that the top block gets its own Euler's formula and the bottom block also gets its own Euler's formula. These can each be rewritten as their own exponentials. Let's call this matrix lowercase lambda. If we take our 4x4 spacetime vector and do a double-sided transformation on it with lambda and lambda inverse, multiplying all the matrix blocks out, we get the expected rotation formulas for each of the 2x2 vector blocks that we saw earlier. In this case, the upper vector and lower parity transformed vector are rotated in the same way. If we do this again, but exponentiating a bivector made of gamma t and a spatial gamma, the lowercase lambda will contain boosts instead of rotations, with a negative exponential on top and a positive exponential on the bottom, due to the parity flip. And multiplying out all the matrix blocks, we get the expected formulas for boosting the 2x2 vectors. Note that the top and bottom vectors boost in opposite directions due to the parity transformation. So all of that might have been a bit confusing, so let's sum it up. When a spacetime vector is written as a column, it is Lorentz transformed with an SO13 matrix capital lambda from one side. When a spacetime vector is written as a 2x2 matrix using sigmas, it is Lorentz transformed with a pair of spin 1,3 matrices L and L dagger on either side. When a spacetime vector is written as a 4x4 matrix using gammas, it is Lorentz transformed with a pair of matrices lowercase lambda and lowercase lambda inverse. These are block diagonal matrices containing the L transformations and the parity transformed versions of L in the chiral basis. We say lowercase lambda is the direct sum of a left spin 1,3 matrix and its parity transformed right spin 1,3 matrix. Now, all these explanations for Lorentz transformations involve a lot of components to keep track of, which is confusing. You may want to watch video 12 on spin groups for a more satisfying interpretation of these exponential formulas that's based on geometry and Clifford algebras. The approach in Clifford algebras is to start by understanding how to reflect an object in a mirror, and then learn that reflecting an object twice is the same thing as rotating it, or boosting it in the case of space-time. And the rotation angle is double the angle between the two mirrors used. Reflecting a vector in a Clifford algebra is done with a negative conjugation operation. Conjugation just means multiplication on either side by an object and that object's inverse. For example, reflecting a vector along the z direction involves negative conjugation by gamma z. Using the standard Clifford algebra rules, it's easy to prove that this operation leaves all the other gammas unchanged, but will give gamma z a negative sign, which is exactly what we expect for a reflection along z. Doing two reflections in two mirrors just means doing two negative conjugations, which is really just a single conjugation with a product of vectors on either side. Using some formula manipulation, we can rewrite these vector products using exponentials of a unit bivector b and theta over 2, which is the angle between the two mirrors. This gives a rotation by angle theta. If the bivector b squares to -1, we get a rotation, just like in the case of two spatial gammas. If the bivector b squares to +1, we get a boost, just like the case of gamma t and one spatial gamma. Now, in this video, I will write out a number of formulas involving the gammas purely symbolically. However, I will often use the chiral representation basis when talking about chirality, and use the mass representation basis when talking about matter and antimatter. So, we've spent a lot of time talking about the gamma matrices and how they are Lorentz transformed. Now let's get back to the Dirac equation. In this video, I will frequently write the Dirac equation simply using the four-momentum vector p. If you want the more traditional Dirac equation, you can always write p as a linear combination of gammas, and then use quantization rules to replace the components of p with IH bar times a derivative. So in the Dirac equation, there are three main objects: the four-momentum, which is a vector, the mass, which is a scalar, and psi, which is a Dirac spinor. If we move the mass term to the other side of the equation, we see the Dirac equation resembles an eigenvalue equation. We normally think of eigenvalue equations as having a rank 2 linear map matrix acting on a rank 1 column vector to produce a rank 0 scalar eigenvalue. But with the Dirac equation, we have a rank 1 vector p written as a matrix acting on a rank 1/2 spinor psi written as a column, which produces a rank 0 scalar eigenvalue mc. Now, you might be wondering why I'm calling psi a rank 1/2 spinor. This is because spinors transform half as much as vectors do. Now, I've shown that a spacetime vector in the 2x2 matrix representation Lorentz transforms with a double-sided transformation of spin 1,3 matrices. I showed in video 9 that we can factor this matrix into a pair of Weyl spinors. As a result, each Weyl spinor transforms using only one spin 1,3 matrix L. The parity transformed version of a Weyl spinor transforms with L dagger inverse, as I showed earlier. A Dirac spinor is just a Weyl spinor and a parity flipped Weyl spinor stacked on top of each other, using the direct sum. So Dirac spinors transform with a block diagonal matrix containing L and L dagger inverse. This is exactly the lowercase lambda matrix we discussed earlier. So let's sum up Lorentz transformations. Rank 1 vectors transform with 2 lowercase lambdas. Vectors are called rank 1 tensors because they have one vector index. This is not related to the concept of a matrix's rank that comes up when discussing linearly independent columns. I call spinors rank 1/2 because they transform with only one lowercase lambda, which is half the transformation that vectors get. This explains why spinors rotate half as much as vectors do. One spinor index is worth half as much as a vector index, because 2 spinor indices correspond to one vector index, as seen with the gamma matrices. Rank 0 scalars don't transform at all when we change coordinates, which is why they are called rank 0. Knowing all this, it's easy to show that the Dirac equation is invariant under a Lorentz transformation. To prove this, all we do is Lorentz transform the Dirac equation and show that it does not change. We Lorentz transform the vector p with lambda and lambda inverse on either side. And we Lorentz transform the spinor psi with lambda from the left. Here, lambda inverse and lambda cancel. And if we multiply both sides by lambda inverse, these both cancel, and we end up with the same original Dirac equation. So the Dirac equation is invariant under Lorentz transformations. The next topic I want to talk about is called chirality. Chirality is a property we assign to an object when the object is not equivalent to its mirror image. For example, a left hand is not equivalent to its mirror image, which is a right hand. Transforming a left hand into a right hand using a mirror reflection is called a parity transformation. Dirac spinors have a similar chiral property, where parity transforming a left spinor will give us a right spinor. We've seen that the lowercase lambda matrix that transforms Dirac spinors is in block diagonal form in the chiral basis. So the top and bottom halves of Dirac spinors transform independently from each other in the chiral basis. Also, we know the two halves rotate in the same way, but boost in opposite ways. So we can exchange the top and bottom transformations by doing a parity transformation, flipping the x, y, z directions so that the boosts reverse. For this reason, in the chiral basis, we say the top half of a Dirac spinor is left chiral, and the bottom half is right chiral. Note that the two halves are not perfect mirror images, which is why I use the different letters psi and phi, because the left and right spinors generally have different components. But doing a parity transformation on a Dirac spinor basically swaps the left and right components in the spinor, so that their roles are switched. If we take gamma 5, which is the complex I times the 4 gammas, in the chiral basis it looks like this. It is also block diagonal, with a negative identity matrix in the top block and a positive identity matrix in the bottom block. If we apply the gamma 5 matrix to a Dirac spinor where only the left half is non-zero, we get the same spinor times -1. In other words, this spinor's eigenvalue under gamma 5 is -1. And if we apply gamma 5 to a Dirac spinor where only the right half is non-zero, then we get an eigenvalue of +1. So we now know how to identify the left and right portions of a Dirac spinor. When we apply gamma 5, the left portion will have an eigenvalue of -1, and the right portion will have an eigenvalue of +1. These properties hold in all matrix representations for the gammas, not just the chiral basis. Using this knowledge, we can define the left and right projectors PL and PR. If we apply PL to a left eigenspinor, The eigenvalue of -1 gives us 1 plus 1 equals 2, and divided by 2 is just 1. So the left half is unchanged by the PL projector. But applying PL to a right eigenspinor, the eigenvalue of +1 gives us 1 minus 1 equals 0. So the right half is removed by the PL projector. The right projector PR is the mirror image of PL. We reflect the XYZ gammas, which has the effect of giving gamma 5 the opposite sign. As a result, PR projects out to the right eigenspinor instead, and sends the left half of the Dirac spinor to 0. So the projectors PL and PR are useful because they let us separate out the left and right chiral halves of a Dirac spinor. The key property of a projector is that a projector will square to itself. So applying a projector once is the same thing as applying the projector multiple times. Adding the two projectors together gives the number 1. This means that adding the left and right portions of a Dirac spinor back together gives us the original Dirac spinor. The left and right projectors also multiply to give 0, which means they are orthogonal. This means that the left and right portions of a Dirac spinor have nothing in common. When we write out these projector matrices in the chiral basis, all these properties look pretty obvious if you look at the matrices for a few seconds. In the mass basis, these properties are still true, but they are less obvious. It's useful to be able to write out these properties using abstract symbols instead of matrices, because this shows the properties are always true regardless of our choice of matrix representation. Next, I'm going to introduce a new way of doing parity transformations that will come up later. We know that taking a vector v and doing a negative conjugation with gamma t will reflect the vector along the time axis. In other words, the time component will get a negative sign, and the space components will stay the same. Now, if instead of doing a negative conjugation with gamma t, we do an ordinary conjugation, we get the opposite. The time component stays the same, but the space components all get negative signs. So conjugation by gamma t is another way of doing a parity transformation. This applies for parity transforming vectors, but it also applies for parity transforming bivectors. If we conjugate both of the vectors inside a bivector, the inner parts will cancel. So this is the same as just conjugating the bivector itself. In fact, if we take an exponential of a bivector and conjugate it with gamma t, if we rewrite the exponential as a cosine plus the bivector times sine, we can distribute the gammas on either side to both terms. The scalar part remains unaffected since gamma t and gamma t inverse cancel, but the bivector part will be conjugated and undergo a parity transformation. So this means that parity transforming an entire exponential is the same thing as parity transforming the exponential's argument. When we parity transform a rotation, the rotation remains unchanged, because a spatial rotation happens in a plane with two spatial directions. But if we parity transform a boost, this does reverse the direction of the boost in space, as we would expect. Here's yet another way of doing a parity transformation. A Dirac spinor is just a left and right Weyl spinor stacked on top of each other using the direct sum. So this transforms with a block diagonal matrix containing L in the first block and the parity transformed version, L dagger inverse, in the second block. This 4x4 matrix that Lorentz transforms a Dirac spinor is denoted as lowercase lambda. Now, taking the Hermitian conjugate of lambda is the same as taking the Hermitian conjugate of its two blocks. And taking the inverse of a block diagonal matrix is the same thing as taking the inverse of its individual blocks. So this means that taking the Hermitian conjugate and inverse of lambda swaps the left and right blocks. So lambda dagger inverse is the parity transformed version of lambda. However, we know that when we Lorentz transform a Dirac spinor using an exponential of a bivector, this can also be parity transformed using conjugation with gamma t. So to parity transform lambda, we can either take its dagger inverse or take its conjugation with gamma t. Both of these give the same parity transformed result. After doing a little rearranging, we also get that gamma t lambda inverse equals lambda dagger gamma t. We'll use these facts later when defining the adjoint of a Dirac spinor. So now I'm going to explain the concept of a Dirac adjoint. For a Dirac spinor psi, the adjoint spinor is denoted psi bar. Psi bar is useful because the product of psi bar and psi will result in a scalar, so this functions as a kind of inner product for Dirac spinors. Basically, under Lorentz transformations, psi will transform with a lambda from the left, and the adjoint psi bar will transform with lambda inverse from the right. The lambda inverse and lambda cancel, leaving the inner product the same as it was before the coordinate transformation. Before we define what this adjoint spinor is, let's review the scalar products for Pauli spinors and Weil spinors that we covered in video 9. We know Pauli spinors in 3D space are rotated with SU2 matrices, which are matrices whose Hermitian conjugate, denoted with a dagger, equals their inverse. If we have Pauli spinors psi and chi that transform with an SU2 matrix U, then their product chi dagger psi is unchanged by this transformation, because the U dagger U term in the middle cancels to the identity. Weil spinors in space-time are Lorentz transformed with SL2C matrices, which are not guaranteed to obey the unitary property. This means that if we have Weil spinors psi and phi, phi dagger psi is not guaranteed to be unchanged. We can get around this problem by defining the scalar product to be phi transpose epsilon psi, where epsilon is some matrix. If we Lorentz transform the Weil spinor using L and demand the scalar product be unchanged in the new coordinates, this gives us the property that L transpose epsilon L equals epsilon. Rearranging, this means that we can turn L transpose into L inverse by swapping its order with epsilon. This basically means we can take phi transpose epsilon to be the left half of the scalar product, which transforms with L inverse from the right. This gives us an invariant scalar product. As shown in video 9, epsilon ends up being this antisymmetric 2x2 matrix here. So Dirac spinors are like a pair of Weil spinors, and transform with a left copy of SL2C summed with a right copy of SL2C. Similar to Weil spinors, we cannot just use phi dagger psi on a pair of Dirac spinors and expect to get an invariant scalar, since the transformation matrix lambda is not always unitary. Instead, we'll use a similar trick as before and introduce a new matrix M in the middle, so our scalar product is phi dagger M psi. If we Lorentz transform our Dirac spinors using lambda and demand that the result is unchanged in the new coordinate system, we get that lambda dagger M lambda must equal M. We can take this formula and multiply both sides on the left by lambda dagger inverse, and multiply both sides on the right by M inverse. This lets us cancel some M's and lambdas, and we get lambda dagger inverse equals M lambda M inverse. But this looks exactly like the equation we saw a few minutes ago for parity transforming lambda using gamma t. What this tells us is that our matrix M is exactly gamma t. So our scalar product for Dirac spinors is phi dagger gamma t psi. We can Lorentz transform this and use the properties of gamma t to show that the scalar product is unchanged after the coordinate transformation. We define phi dagger gamma t as the Dirac adjoint of the spinor phi, written phi bar. This is like the left half of the scalar product for Dirac spinors. As we saw before, gamma t basically has the effect of changing lambda dagger into lambda inverse if we swap its order with gamma t. This means the Dirac adjoint spinors transform with lambda inverse from the right. Now, I want to talk a little more about what this gamma t does to Dirac spinors. We know that if we have a left chiral spinor, its eigenvalue under gamma 5 is -1. However, if we apply gamma t to this left chiral spinor, it behaves more like a right chiral spinor. Applying gamma 5 to gamma t times a left spinor, then swapping the two gammas gives us a negative sign. And the -1 eigenvalue cancels with this to give +1. So gamma t times a left chiral spinor has an eigenvalue of +1, just like we'd expect from a right chiral spinor. Now, gamma t isn't too special here. The other gammas also have this property. But gamma t is special because it reverses the direction of boosts. If we boost gamma t times a left chiral spinor, swapping with gamma t has the effect of reversing the boost. So this boosts just like a right chiral spinor. And the opposite is true for right chiral spinors. Gamma t will change its +1 eigenvalue into a -1 eigenvalue and also reverse boosts. So gamma t basically exchanges left and right chiral spinors. The fact that gamma t swaps the left and right halves of a Dirac spinor becomes more obvious when we write it as a matrix in the chiral basis. As a reminder, psi L is a Dirac spinor with only the left half non-zero, which I've denoted by two chi components here. And psi R is a Dirac spinor with only the right half non-zero, which I've denoted by psi components here. The full Dirac spinor psi is the sum of its left and right parts. The gamma t matrix in the chiral basis looks like this, with 2x2 identity matrices as off-diagonal entries. It's obvious that this swaps the left and right halves chi and psi, but it's important to remember that gamma t swaps the left and right halves in all matrix representations, since we've proved it symbolically without referring to any specific matrix representation. Next, I'm going to talk about the Dirac equation's conserved current. We know that psi bar psi is a scalar that's invariant in all coordinate systems. But given any vector v, the combination psi bar v psi is also a scalar that's invariant in all coordinate systems. This is easily checked using our Lorentz transformation rules. We can use this to define four numbers, psi bar times one of the four gammas times psi. These four values form the four components of a current density 4 vector. And these components obey a continuity equation, where changes in density of the time component always result from a divergence or convergence in the spatial current densities. To prove this, we start with the Dirac equation and expand the vector p as a linear combination of the gamma basis vectors. Then we take the Hermitian conjugate of both sides. On the left, taking the Hermitian conjugate of a product means writing the product of the Hermitian conjugates in the reverse order. And on the right, mass is a real scalar, so the Hermitian conjugate doesn't affect it. Now, the p components are also scalars, so we can just slide them past the gammas since the order doesn't matter. Now, taking the Hermitian conjugate of a gamma matrix is the same thing as reversing the spatial gammas. So this is a parity transformation. And as we learned, a parity transformation can also be done with conjugation by gamma t. Multiplying both sides by gamma t on the right, we can cancel and slide gamma t past the scalar p components. Now we can replace psi dagger gamma t with psi bar. This is the adjoint version of the Dirac equation. Now, when we take the adjoint Dirac equation and apply quantization rules, when we Hermitian conjugate the derivative operator, it causes the derivative to act to the left. So I'm using this left arrow to remind us of that. And the dagger applied to the complex I gives us its complex conjugate, which is negative I. Dividing by IH bar, we get this version of the adjoint Dirac equation. So we have the standard Dirac equation, which I've divided by IH bar, and the adjoint Dirac equation. We can multiply the Dirac equation by psi bar from the left, and multiply the adjoint Dirac equation by psi from the right. I'm also going to switch the upper and lower indices in the summation, but this doesn't change the meaning of the formula. Now, if we add these two equations together, the mass terms with opposite signs cancel. If we apply this adjoint derivative to the left to psi bar, the result looks like the result of a product rule, assuming the gammas are constants. So we can undo the product rule and write the formula as a single derivative. This proves the 4-vector psi bar gamma psi obeys a continuity equation, and does indeed represent a conserved current, often written as J. This current can sort of be treated as a probability density for a one-particle system, but in quantum field theory, this is treated as a charge density instead. Also note that this conserved current can also be derived using Noether's theorem. The last thing I'll do is talk a little bit about matter and antimatter. So we've already seen that gamma 5 helps identify the left and right chiral halves of a Dirac spinor. These are the eigenspinors of gamma 5 with eigenvalues of +1 and -1. And gamma t swaps the positions of the left and right eigenspinors. But let's consider the opposite case. Let's look for eigenspinors of gamma t with eigenvalues of +1 and -1. I'll call these eigenspinors psi plus and psi minus. If we take psi plus gamma t psi and apply gamma t to it, after we distribute, gamma t squared goes to +1, and we end up with the original expression. This means psi plus gamma t psi is an eigenspinor of gamma t with eigenvalue +1. We'll call this eigenspinor psi plus. Similarly, if we take psi minus gamma t psi and apply gamma t to it, we get the negative of the original expression. So psi minus gamma t psi is an eigenspinor of gamma t with eigenvalue -1. We'll call this eigenspinor psi minus. Let's see what these look like as arrays in the chiral basis. If we write the left and right halves of psi as chi and psi, we know gamma t swaps the left and right halves. So the psi plus eigenspinor has left and right halves that are equal. Meanwhile, with psi minus, the top and bottom halves have equal size, but have opposite signs. We can also show that applying gamma 5 to psi plus makes it look like psi minus with the opposite sign introduced. And it makes psi minus look like psi plus, having identical signs. So given a Dirac spinor psi, we can either break it up into left and right halves, or plus and minus halves. The left-right decomposition can be thought of as a linear combination of these two basis spinors, which are eigenspinors of gamma 5. This is the chiral basis. Although keep in mind both chi and psi are two-component Weyl spinors, with the two components representing the spin up and spin down states. So these are really four-component Dirac spinors, but we're writing them in this compressed notation for convenience. The plus-minus decomposition can be thought of as linear combinations of these two basis spinors, which are eigenspinors of gamma t. This is the mass basis. For the mass basis and its coefficients, I've introduced factors of 1 over the square root of 2 for normalization purposes. We'll see in the next video that the plus component is related to matter, and the minus component is related to antimatter. So matter and antimatter are really linear combinations of left and right chiral spinors. The change of basis equation between the components in the chiral basis and the mass basis is given by this matrix U. So changing a column spinor from the chiral basis to the mass basis is done with a single-sided transformation with this matrix U. Since the gammas are spacetime vectors, changing a gamma matrix from the chiral basis matrix to the mass basis matrix is done with a double-sided transformation with U and U inverse. It turns out that in both the chiral basis and the mass basis, gammas x, y, and z look the same. However, gamma t and gamma 5 sort of switch roles. We can see in the chiral basis, gamma 5 gives eigenvalues for the top and bottom halves of the Dirac spinor, which are the left and right halves, and gamma t swaps them. But in the mass basis, when gamma t gives obvious eigenvalues for the top and bottom halves of the Dirac spinor, these are the plus and minus halves in the new basis, and gamma 5 swaps them. As an aside, it's also easy to show that we can invent plus and minus projectors with gamma t, which project out the plus and minus halves of a Dirac spinor. And this works in all matrix representations. So to summarize this video, the Dirac equation is a relativistic wave equation that we get when we take the mass-energy-momentum relation from special relativity, quantize it, and take its square root, which can be done using the algebra rules from Clifford algebras. Psi ends up being a Dirac spinor. The gammas in the Dirac equation are a new way of writing the four spacetime basis vectors, and they come from Clifford algebras. Four-component spacetime column vectors transform with an SO13 matrix, capital lambda, from one side. 2x2 spacetime vectors written with sigmas transform with a pair of spin-1,3 matrices, L and L dagger. 4x4 spacetime vectors written with the gammas transform with a pair of matrices, lowercase lambda and lowercase lambda inverse, which are direct sums of a left spin-1,3 matrix and a right spin-1,3 matrix. We've learned that Dirac spinors can be broken into left and right chiral halves, and we can swap back and forth between them using a parity transformation where we reverse the XYZ directions. We also learned other methods for doing a parity transformation involving gamma t. We also defined the Dirac adjoint spinor, which lets us do scalar products with Dirac spinors. And we also used it to define a conserved current for the Dirac equation. Finally, we learned that matter and antimatter are superpositions of the left and right chiral parts of a Dirac spinor.